Hello? Yes?
Yeah.
Sit. Sasha, can you hear us?
I can hear you. I cannot see you because I can see only my screen.
That's fine. I mean, hopefully everybody here will sit down now and we can start the talk.
Yeah, okay. Just let me know when to start.
I think the speaker is a bit too loud. Okay. So I think for the next talk, we're ready. And we're very happy to have Alexander Bobenko from Berlin, who will talk on dimers and M curves, as you can see.
Okay, thank you very much. Can you hear me well? Yes. I'm very pleased to be at that conference, also virtually. So it's a great event. I'm very glad to be at the conference dedicated to Igor Krichever because my research was very much connected to what he did, and he influenced my life. And the results I'm going to present today are also amazingly very much related to his works. And this shows, of course, how deep his works were. So I will give a talk on our joint results with Nikolai Bobenko, who is in the room, and with Suris, who is not. So there are two papers. One exists and one will be existing in a week on dimers and M curves and on limit shapes. So my talk is based on these results. So, and of course, it's very convenient to give a talk right after Alexei. So because he explained a lot, and my talk will be essentially about the same things, but completely from different perspective. Yeah. So I will start somehow at the point where he ends, and we will come back to the starting point of his talk. So the problem we are going to consider is the problem with dimer models. And news here. So we are on a graph. We are consider perfect matchings, but all these things were explained very well in the previous talk. And so we are looking at the probabilities of dimer configurations. So the weights are defined on the edges. It's very important in this talk that these weights, the probability weights for the edges, are not all equal. They will be rather complicated functions, and I will explain how they are how they can be specified. So the weights on the but we are going to come from this Riemann surface theory to statistical mechanics, and therefore it's important to learn what is important, what is only mathematicians, what is only mathematics. So the weights which are physical are the weights on the faces of this dimer configuration, and they're given by this formula. And although physically all the weights on the edges are assumed to be real and positive, they can be complexified in a way that the face weights remain complexified. And this is a famous Castellan condition which prescribes us the sign of this face weight. It's real with this side where n is the number of pairs of edges around the face. And if this condition is satisfied, then the model is physical. Yeah. So I will not go here into detail because, as I promised, we start with mathematics and then we'll come to results with dimer models. So what kind of geometry, what kind of dimer configurations we are considering? So we are considering bipartite graphs with white and black vertices. And then there are parameters associated to these weights, and they are labeled by these train tracks, which are shown here in the picture. So we are interested in integrable systems, and these are the features of integrable systems. So here we see just one edge with two parameters, alphas and betas, associated to this edge, and also a phase, how these train tracks are arranged around the boundary of this phase. So now let us discuss the problem we are going to solve. So as in the previous talk, we will mostly consider the square grid lattice, because that's the most interesting and also provides us with all essential properties of the models. So you simply consider planar bipartite doubly periodic graph. In our case, it's a square grid with white and black vertices with two sublattices. And one considers a fundamental piece of such a square grid and assumes that there are some periodic weights associated to the edges of this graph, of this lattice. These weights generate a so-called Castellan matrix, K. So the entries of this matrix are just these weights. And then what you can do, you can define the so-called spectral curve. So you see here in this picture, this is a fundamental piece of your weights. And then you put, you multiply the weights sitting here with Z, weights sitting on these edges with W. And this is your Castellan matrix with spectral parameter. So when you solve the direct problem for dimers, then what you consider the eigenfunctions of this modified Castellan matrix, because and look at Z and W that have a non-trivial function psi. So of course, in this case, the determinant of K should vanish. And this is the determinant of KZW is an equation for the spectral curve. So in this case, that's the way how you generate Riemann surfaces, how you generate spectral curves, just by considering of periodic weights. These are classical results and well understood. So the main object here, I'm coming to this inverse problem, will be the eigenfunction. So this eigenfunction was just defined. It's a function on the Riemann surface on the spectral curve. And the monodromies of these functions, how it varies when you go here from left to right and from right to left, are just these Z and W or complex parameters, which you take from the spectral curve. So what is important here, what you can analyze analytic properties of this psi function on the spectral curve, just from this classical description. So, and this is a direct problem for dimer models. You have your weights, periodic weights, you generate Castellan matrix, you generate spectral curve, and then you consider the eigenfunction on this spectral curve. So I will be talking about the inverse problem. So now you consider this problem from the right to the left. So, and this is the approach which is very much related to Krichever. So you can now set up the problem in a completely different way. You say, I have a Riemann surface and a function with some analytic properties on it, with some prescribed analytic properties. You've learned about these analytic properties by analyzing the direct problem. But now you become a little bit more general, and you say, my data are Riemann surface and this psi function or some analytic data for this psi function. From here, you can construct this function explicitly. Yeah, there is an explicit representation for this function. And then when you know it, you can derive the formulas for the weights from there. This is an inverse problem, which is known as a Krichever scheme. In this approach, the weights you obtain are more generic. They are not necessarily periodic. They are quasiperiodic, but they include all these periodic weights. So, and let me just, I'm very pleased that here, so I can mention a paper which really influenced my life. Yeah. So this is a paper by Igor Krichever, where he came up with this Krichever scheme in 1977. Yeah. So I was a second-year student at that time, and that was one of the first, if not the first paper I read, scientific paper I read. So the paper was about the KP equation, which is written here. And this was exactly the case where this Becker here as a function approach was clearly formulated and invented. You start with Riemann surface, you start with some analytic data on this Riemann surface, and construct Becker here as a function, which has very special analytic properties. This is a function which is meromorphic on the Riemann surface beside one point, where it has an essential singularity of prescribed type. This essential singularity depends on parameters of this KP equation and some pole divisor. These are the data, these are Krichever data. So, and then this function, it turns out it can be constructed explicitly. There is a formula for this. And as soon as you have formula for this psi function, you can derive from there a formula for the solution of a KP equation. So that was the first case when this approach was applied to a general Riemann surface. There were several cases which were studied before by Matveyev, by Dubrovin, by Novikov. It was essentially the Kartavik-de Vries equation, or nonlinear Schrödinger equation, Sine-Gordon equation. But that was the paper where Krichever's scheme appeared, and it became very, very influential because it can be generalized, it can be specified for various Riemann surfaces, and that was the way how you can generate many, many integrable systems and obtain their solutions. So in a way, what we do with these diamond models, we apply this Krichever scheme to diamond models. So diamond inverse problem, and this is Becker here as a function. I believe that you've learned a lot about this function in lectures of Samuel Gruszewski. Yeah? So in a way, my talk is between his lectures and the lecture Alexei just has given. So what are the data? So we start with Riemann surfaces. We have a compact Riemann surface, and on this diamond graph, we introduce the train track parameters. Now, these parameters alphas and betas that are labeled of these train tracks, they're just points on our Riemann surface. Then you construct a meromorphic function on the Riemann surface. This Becker has a function with prescribed analytic properties. This function is defined at all black points of your graph. And the analytic property is the following. As soon as you cross a train track, then this function psi becomes a zero or a pole. So it's a meromorphic function on the Riemann surface, and its divisors are well defined. So as soon as you have these analytic properties, you can write a formula for this function, which is quite similar to the formula of Krichever in the KP case. But now the function is meromorphic, and such formulas and such meromorphic Becker-Hilse functions appear in analysis of discrete integrable models. Yeah, so I will not explain all these ingredients, what are thetas, what are e's. Yeah, thetas are standard theta functions. E is prime form. But there is an explicit representation for this. So now it turns out that these functions are linearly dependent. If I consider a star associated to a white vertex, so all neighboring black vertices, then there is such a Becker-Hilse function sitting at all these black vertices, and they are linearly dependent. You can see this just analyzing their analytic properties. And exactly as in the KP case, from here, you can compute the corresponding coefficients, which are now independent of the point of your Riemann surface, but depend on these parameters alphas. And these are nowadays are called Fock weights. There is an explicit representation for them similar to the representation for the solution of the KP equation. So just an explicit formula for the weights. So as a side remark, yeah. So if you play this game just for a triangle, then you obtain this Dirac equation for 3 Becker-Hilse functions. And then if you write down this Dirac equation explicitly, you end up with a famous Fay identity. So in a way, it's also a very simple way to prove Fay identity. So I assume that this identity played a crucial role in the lectures of somewhere. So this identity is here. Okay, so now we are going in the direction of statistical mechanics. That was complex analysis up to now. And what is important, we would like to have these weights real and positive. And then what one can do? So one should specify the Riemann surface. It should become a real Riemann surface with an anti-holomorphic involution. And in this case, to get positive weights, you should take an M curve. An M curve is a Riemann surface of genus G with a maximal possible number of real ovals, G plus 1. So here in this picture, you see 1/2 of this Riemann surface. Yeah. So it's a simply connect. It's a flat planar domain with 2 holes here. All the boundaries are around. You take 2 copies and glue them together along the boundaries. You get a Riemann surface, and this Riemann surface is your M curve. Or you just make an inversion, which is indicated here by tau, with respect to one of these circles, x0. And then you generate the picture on the whole complex plane with the holes x1 and x2. And then you have R plus and R minus, two halves of your Riemann surface, and they're glued together into one compact Riemann surface, which is an M curve. I should stress here that, okay, we end up with this picture for an M curve. And I should stress here that this is not just a picture. This is not an illustration. This is a Riemann surface, what you see here. So you have circles, you have centers of these circles, you have radii, and these are real parameters that define you the complex structure on your Riemann surface. The complex coordinate here is just this complex coordinate z. So you identify the screen of my laptop with a complex plane, and the complex coordinate on this surface is z. So so this means that it's not only an illustration, you can make computations with these pictures. And that's exactly what we did. And I maybe should emphasize that all figures in this talk are not just hand-drawn. They are computed. There will be several figures here. Okay, now we've learned what is an M-curve, how one can uniformize it, how one can represent it in a way that is numerically treatable. And all these train track parameters, which you remember were the points on the Riemann surface, they are now, they should sit just on one of these real ovals. So, for example, on this real oval x0 on the unit circle. So if you choose these alphas this way, then all the phase ways become real. This is a reality condition. But we have one more condition, that the sign of this real number of all these ways should satisfy the Castellan condition. And this is the ordering condition for these points, alphas, on the real oval x0. So in general, this condition was investigated on minimal graphs by Boutillier, Cimasoni, and Detillier. For g equal to 0, what we get here, we have no x1, no x2, just x0. And for g equal to 0, you end up just with isoradial weights. So that's the case which was investigated and solved by Kenyon and Okunko. Okay, so but now let us come back to our square grid, simplify the picture a little bit. And that's a picture in the case of the square grid. So we have these train tracks parameters alphas plus and minus, and train track parameters betas plus and minus. And then if you look what is this Castellan condition, then you get this result at the right-hand side. So as I said, all the points on your Riemann surface should lie on one real oval. I mean these train track parameters. You see them here shown in colors, alpha minus, alpha plus, beta plus, and beta minus. And moreover, they should be clustered in such a way that all beta minus, all beta plus, all alpha minus and alpha plus belong together. They are not separated by other points. And moreover, these four sets, they are ordered in the way how it is shown here. So alphas separate betas. Alpha sets separate beta set. And then your weights are positive if and only if the corresponding Riemann surface is an M curve, and the labels are chosen satisfying this clustering condition. So the same thing you can do on the hexagonal grid, which also hopefully will appear at the end of my talk. And then you have obviously 3 different kinds of train tracks, alpha, beta, and gamma, and they should be also clustered in a similar way. All alphas belong together, all betas and all gammas, like in the picture you see here. So this means that what we are doing here, it's not just complex analysis, this is statistical mechanics, because all the weights satisfy this positivity property. Good. So, and now just let me show the formulas you obtain this way. So these are the formulas for the phase weights. They are expressed in terms of theta functions. What is involved here are the train track parameters and integrals on the Riemann surface between the corresponding points on the Riemann surface. Yeah, so maps like the integral of Abel map from alpha I to beta I and stuff like this. Yeah. So these prime forms, which appeared in the formulas for the Fock weights, disappear in the formulas for the phase weights. So if now you do some computations, and I promised you to explain that how it is possible, so then you obtain pictures like this, and these are the phase weights on square grid diamond models. So in the case of genus 1, you obtain a picture like this. In the case of genus 2, you obtain pictures like this. And we have seen a lot of such pictures in the theory of integrable equations. So if you want, you can see this as waterways, as interacting waterways, as integrable interacting waterways. In the case genus equal to 0, we again end up with isoradial weights. So all functions become rational functions. We are on the Riemann surface of genus 0. If you are back to a doubly periodic case, then you recover the spectral curve. It's the result by Kenyon-Okounkov-Sheffield, and the corresponding Riemann surface turns out to become a Harnack curve. So, but the weights we are considering here, and that's exactly the same case with Krichever solutions for the KP equations, are not necessarily periodic. They are quasiperiodic. They came from this linearization on the Jacobi variety, and this linearization hyperplane or linearization 2-plane can cross the Jacobi variety in such a way that we do not pass through the rational points, and then it's irrational. So in this terminology, you see our parameters are an M curve, and these points, alpha plus, alpha minus, beta plus, and beta minus, the weights are periodic if and only if these two divisors, alpha minus minus alpha plus and beta minus minus beta plus, are principal divisors. So they are divisors of some meromorphic function. One should also mention that in the case when genus is non-zero, and even in the case when these train track parameters repeat periodically, the weights, these weights, the Fock weights or the weights for the phases, are not necessarily periodic. Yeah, but they are quasi-periodic, and in this case, you can obtain similar results as in the periodic case, and I will explain this. Yeah, so they appear quite natural in this approach when you start with a Riemann surface. Okay, so that's what kind explains to us what kind of models, diamond models, we are considering. And now let us go a little bit more in detail into this algebra-geometric description, which appears here. So the goal is, as Alexei has explained, is to describe limiting objects in treatable form so that we can really compute the corresponding characteristics of diamond models. So in this case, we describe them using these algebra-geometric terms. Okay, what are our data? These are so-called Harnack data. It's an M curve with an anti-holomorphic involution, tau, which I have explained already. In this picture, it's a reflection with respect to the unit circle. And with parameters, with points on our Riemann surface, alpha plus minus, beta plus minus, that satisfy the clustering condition. So okay, again, the data you see in this picture, they're real data. So you just take this point, take this Riemann surface, and compute. Okay, now one introduces two normalized meromorphic differentials with simple poles at these points, alphas and betas, with residues equal to plus minus 1 at these points, and its zeta 1 has singularities at alpha plus minus, and its zeta 2 has singularities at beta plus minus. They, of course, are defined up to holomorphic differentials, but you normalize them and in a unique way, just requiring that the A periods, all A periods vanish. And A periods on this Riemann surface are circles going, or cycles going around these circles. So these differentials are well defined. Now you take such a differential and integrate it and obtain an abelian integral. And since these periods, the A periods, vanish, this abelian integral is well defined on this 1/2 of our Riemann surface on R plus. You just choose your starting point, starting integration point, and then it doesn't matter how do you integrate. Yeah, so it's well defined up to a constant. Okay, now we have two differentials, and we have two integrals, two abelian integrals. Let us denote the real parts by x's and the imaginary parts by y's. And then we are back to one more recent paper by Igor Krichever, who has considered this case and who has proven that these coordinates, if you take two x's, x1 and x2, or y1 and y2, they can be treated, they are coordinates on the R plus without the boundary. So that's this 0 here. Yeah, so on this open set. So you can use x's as coordinates on R plus, or you can use y's as coordinates on R plus. And for some historical reasons, s's, which are almost y's, are canonically used in the doubly periodic case, and therefore they will appear both y's and s's, but it's almost the same thing. So now we have two coordinates on this R plus Riemann surface, and we end up with the following picture. So again, this is our Riemann surface with the data. X's are well defined here, and there is a diffeomorphism of x's to some subset of R2, and the image of R plus is the amoeba. On the other hand, if you consider S's or Y's, which is more or less the same thing, you map the interior of this disk or R plus to a polygon, which is called a Newton polygon in the periodic case. So these boundaries are mapped to 2 points inside Newton polygon, and they are mapped to some internal inner ovals of amoeba, so as shown in this picture. Again, this is a computed picture, so this is exactly how it looks like. Okay. So now, what can we do with this? Yeah, how one can use this? First of all, we are going to define Ronkin function and surface tension. They are both very important in variational description of dimers. Ronkin function is free energy, as Alexei has explained, and surface tension is the functional which should be minimized to get this height function as a solution of the corresponding minimization problem. So in this approach, one can obtain new formulas for Ronkin function and for the surface tension. So C1 and zeta1 and zeta2 are two differentials, that zeta1 and that zeta2. Zeta2 is an integral which is well defined on R plus. Zeta1 is differential. So you build such a product, integrate it from somewhere to the point on your Riemann surface. This point has coordinates x1 and x2. And now you take the imaginary part of this, and this is a function. This function now is called the Ronkin function, and you play the same game with the surface tension function, almost the same thing. It's Lejeune transformed, but treated in terms of other coordinates, not in terms of coordinates x's, but in terms of coordinates y. So they are Lejeune dual, and they satisfy the following conditions. If you take gradient of sigma, then you recover the coordinate x's. If you take gradient of rho, you recover s's. So, and this definition agrees with algebraic ones in doubly periodic case. So this case is, we are considering as more general. It's not doubly periodic. There is no spectral curve. There is only the Riemann surface. But if you consider the doubly periodic case, then it's possible to show that this Ronkin function coincides with this Ronkin functions, which again appeared in the talk by Alexei, and which is due to Kenyon, Alkunkov, on Sheffield, where your integrate log of this polynomial of your spectral curve along a two-dimensional torus. So with respect to x1, which is fixed by x1 and x2. So it coincides up to an affine function, because you can show that the Hessians coincide. And fortunately, this affine function is not important for variational principles, because if you change rho or sigma by an affine function, it doesn't change your variational principle. So therefore, you can equivalently use this Ronkin function, or you can use this Ronkin function when you consider variational problems. So, and for our purposes, this one is much more useful, because you can analyze the convergency and many other things. And this is an integral along the Riemann surface. Here, it's an integral over two-dimensional torus. Okay, now we have extended this picture with two more maps. The gradient of rho is a map from amoeba to the Newton polygon, and gradient of sigma is a map from Newton polygon to amoeba. So that's a dictionary. So in the doubly periodic case, you have a spectral curve, you have these functions z and w that can be treated as a monodromies of the Baker as a function. Main differentials are dz over z, dw over w, and the amoeba map is given by this formula. So in our slightly more general setup, we have an M curve, we have the monodromies of psi function, we have two differentials, and we have this amoeba map, which is given in terms of billion differentials. Okay, now about height function. So, well, Alexei has explained that the height function is in bijection to dimer configuration. So you can analyze height function, and then this means that you analyze the corresponding dimer configuration. Boundary conditions are purely combinatorial deterministic. And it was proven by Kenyon and Prop that the limiting height function converges to a minimizer of this integral. So h is a height function, sigma is a surface tension, you minimize this integral, and then you get the answer. So we are in a more general situation with with quasi-periodic weights, and sigma is defined a slightly different way. But we were able to prove that this is still true for quasi-periodic weights, which are used in our approach. So the limiting height function is again a minimizer. So how does this minimizer look like? Yeah, so this is of course the most important problem. And as Alexei explained already, jointly with Thomas Berggren, they gave answer for periodic weights for Aztec diamond. So we will have a look on this problem in this slightly more general approach. And we were able to give another proof of this, which is purely variational, which is based on this variational description of limiting height function. And also, well, of course, it's very interesting to generalize this to more general boundary conditions. And in some cases, you can do also, as Alexei also has said, it's not an automatic thing. You should invent something. You should guess some analytic properties, or it's some creative work anyway. Okay. Now we will extend this general picture, which we will have, to include dimers, to include Aztec diamond. So the first definition of complex structure on dimers was obtained in the work by Kenyon and Koff, which is 2005. But for us, a very crucial result is due to Berg and Borodin, who have considered the following integral. So d zeta 1 and d zeta 2 are two differentials, which I have already defined. U and V are parameters on the Aztec diamond. And d zeta 3 is a differential which is responsible somehow for the boundary conditions. So if you look at analytic properties of these differentials, then they are chosen as follows. D zeta 1 has singularities at alphas, d zeta 2 has singularities at betas, and d zeta 3 has singularities at all of them, and it's not a linear combination of d zeta 1 and zeta 2. So these singularities are chosen in the following way. Yeah. So now you can compute the number of poles and zeros of this differential d zeta, which depends on u and v. Then from some simple consideration, you can find out how many zeros you know quite well where they are. And it turns out that around the two zeros which you do not know quite well where are they located, and these are so-called free zeros. So one can define a liquid region. This is point in your dimer model configuration when these two free zeros lie. They have to be mutually conjugated, complex conjugated, and they lie in this Riemann surface R0 plus and not on its boundary. That was the result again by Bergen and Borodin, who have shown that there is a diffeomorphism from R plus 0 to the liquid region of the dimer model. And this is a definition of a complex structure on the liquid region of a dimer model, which which comes from the Riemann surface. So that now the picture is complete. You have an amoeba, you have the Newton polygon, and you have your dimer model. And at the center of this, you have this M curve and three diffeomorphisms, X, S, and UV, to amoeba, to Newton polygon, and to the liquid region of your dimer model. Okay. So, okay, this sounds a little bit complicated, but let me show how it works in the simplest cases. For example, for isoradial case, you can write these differentials explicitly, zeta1, zeta2, zeta3, and then you get the parameterization of all these Arctic curves in terms of Vronskyans of these quite elementary functions. This is, of course, not new. But now let us generalize a little bit. Yeah. So this height function was an imaginary part of this integral del zeta. So now let us take its real part, consider its real part as well. So h is defined as this integral, and you have the real and imaginary part. And then it's easy to show that the gradients of g and h are exactly x's and s's. They are maps to the amoeba and to the Newton polygon. So we have seen this already partially. H can be extended affinely to holes and frozen regions. And the theorem is that H is a surface tension minimizer. So again, you consider this surface tension functional in this general setup with Riemann surface. You minimize this functional and get H, which comes from here. Of course, it's not the way how you generate this H, not by minimizing this functional, but what you can do, you can prove that H defined in this way will be the minimizer of this functional, and this means that it's a solution of this dimer problem. Maybe I will say a few words about the proof later, but amazingly, you can consider the dual problem in quite similar way. So, and this G, which is a real part of this height function, is a magnetic tension minimizer. You minimize not the surface tension, but the Ronkin function. So, and play the same game on slightly different set of functions. And here you can prove that G is a magnetic tension minimizer. G, which is here. So that's gives us two more arrows in this diagram. So now the diagram is complete. So there is the map to amoeba, there is a map from dimer to Newton polygon, and these both are described variationally. So in a more general setup, when you have a Riemann surface shown here, you also can do all computations. That all formulas can be effectively computed via Schottky uniformization of the M curve. Again, now this is your Riemann surface. Schottky group is generated by inversion in all these circles. This is a group. You sum over this group the things you had in the genus 0 case, and these are the formulas for these meromorphic differentials we have defined. They are given by this Poincare theta series, which can be computed. So now let me show you the result. So that's a picture for an Aztec diamond. What you can do now, you can take this M curve, compute all the weights using this zeta function representation, and then simulate the corresponding diamond model, and you end up with these pictures. And white curves you see here, they were the limiting shapes computed as I have explained to you. Yeah, so you see they fit quite well. Okay, how much time do I have?
Just a couple minutes, maybe 5 minutes.
I can't hear you.
About 5 minutes.
5 minutes, yeah? Okay, thanks. So the proof idea is minimize this functional. You consider the Euler-Lagrange equation and show that this H, which we have since satisfy this Euler-Lagrange equation in the liquid region, but it's not the end of the story. Yeah? So the problem is that the surface tension is non-differentiable. It has conical singularities, and then it makes some problems to prove that what you have obtained is indeed a minimizer. So you should treat generalized Euler-Lagrange equations in terms of subgradients. In the genus 0 case, this has been done in the recent paper of Astala, Duzet, Krause, and Song. And what we did, we have proven this in the general case of genus 0. So it's not quite obvious how to extend this function G to interior, to the gas region in this case, yeah, to the gas bubbles and frozen regions. But this can be done. It should be done in the following way, that the gradients of this function lie inside the corresponding complementary components of the omega. So here there is some work. So, and maybe at the end, very end, I will show you a couple of slides so that other problems also can be solved in a similar way. This is a hexagonal case. This is a picture of the Riemann surface. Again, this is the Riemann surface, not just the picture, which has holomorphic symmetry, which respects this symmetry of the domain. This is the genus 0 example. This is example of genus 2. And again, you see the map. Now our Riemann surface we are considering here is ramified covering of a Riemann surface. And these holes here, these round holes, are again mapped to the gas regions of our diamond model, and there is a one-to-one map to the liquid domain. So maybe the last, that's a picture in the hexagonal case. Now our Riemann surface is a double cover. The weights live on the factor of this double cover, and you have diffeomorphism to the dimer liquid domain here from the double cover, and diffeomorphism to the amoeba and to the Newton polygon from this factor where the weights live. Yeah, so that's probably the last slide of my talk, which shows us that you can investigate also how these gas regions behave, how they can come together and become hexagonal. And this is a case of ramified Riemann surface, ramified covering. This is the degenerate case, and this is an unramified Riemann surface. So I just announced some results on these limiting shapes, but there will be a talk by Nikolai at another conference, and I hope he will be able to provide you with much more results and much more proofs. Yeah. Okay. So summarizing, I wanted to say at the end, yeah. So that this was really surprising for me. So how well this Krichever scheme fits to the investigation of these Dimer models. And I was surprised to see that we've learned from him from his 2014 paper, where he has considered generalizations for amoebas, also in this more general setup. So this is really an application of what Igor did to this Dimer models world. And I think this is just a beginning, yeah? So because, well, there is very beautiful mathematics. I don't know how interesting it will be for statistical physics, but it's clear that similarly to the finite gap integration theory, you can specify Riemann surfaces, you can specify your models, you can specify your boundary conditions and obtain much more results. So the mathematics of Igor is, I think, very influential and very productive. Thank you very much.
Questions? You will need the microphone. Any questions? I think we also have a chance to ask Nikolai in person later.
Yeah. Ask Nikolai, yeah.
We will, don't worry. Okay, I think people are tired. Let's thank Alexandra again.
Okay, thank you. It was a pleasure.